In this lab, we were tasked with using a pH probe to determine the pH of dilutions. First, we had to calibrate the meter using a 2-point calibration. A 2-point calibration is a method of adjusting the pH meter to two different pH values using a 7 pH buffer and either a 4 pH buffer when the solution added is an acid or a 10 pH buffer when the solution added is a base. First, take the electrode out of the storage solution and rinse with distilled water. Then, put the electrode in the 7 pH buffer, stir, and set the pH meter to 7. After that, rinse the electrode with distilled water again. Put the electrode in the 4 pH buffer if testing acids or 10 pH buffer if testing the bases, stir, and set the pH meter to the according pH. Then, the meter is ready to use. Using buffers with known pH to calibrate the probe provides stable reference points while using the pH meter and ensures that readings are precise. Cleaning and storing the probe is also important. Properly cleaning and storing the pH meter maintains accuracy and the lifespan of the tool. Incorrect maintenance may result in incorrect data the next time it is used. If a pH probe is not stored with enough solution, it will dry out and the gel coating on the bulb is lost, leading to inaccurate and erratic measurements. Once the meter was calibrated, we measured the pHs of the solutions presented for each exercise. First, we rinsed the probe off with distilled water and dabbed it dry carefully with a Chem wipe. Then, we dipped the probe into the buffer solution to test if it was working correctly. Repeating step 1, we measured the pHs of our solutions accordingly. It is important to note that we did this for every solution. One of our exercises also required us to make a buffer. A buffer is a solution whose pH does not change when a limited amount of an acid or base is added to it. A buffer either contains a weak acid and its conjugate base, or a weak base and its conjugate acid. When a strong acid is added, the weak base component of the buffer neutralizes and forms a weak acid. When a strong base is added, the weak acid component of the buffer neutralizes and forms a weak base. We collected pH versus volume data for every solution and every exercise for this lab, using the same procedure of rinsing the probe and dabbing it with a Chem wipe. We recorded the data of the HCl solutions and unknown acid solution from the second exercise in our lab notebooks as well as in our in-class assignments. HCl is a strong acid, while our unknown acid was a weak acid. Strong acids dissociate completely in aqueous solution, which have a large Ka value. Weak acids partially dissociate in an aqueous solution, having a small Ka value. The difference between these two when put into solution is that in a solution, all the H plus ions are released when a strong acid dissociates. Weak acids partially release ions into the solution. This means that at equilibrium, the high H plus ion concentration in a strong acid solution causes the formation of hydronium ions to be much greater than the weak acid solution. Partial dissociation allows the equilibrium system to have a forward and reverse reaction. At the end of the lab, we remembered to wash all our glassware and return it to its correct storage. Our pre-lab assignment detailed all the solutions could go down the sink with plenty of water. Thank you for watching.